Can folks in the chat hear me now? Thanks. Okay. All right, folks. So as usual, remember to do the seating survey. CAM 112, Section 002, ILC 118. Let me get this up here. Okay. Small group activity number 3 is due today at 5 o'clock. I have also released a sample exam style kinetic simulation spreadsheet and a tutorial video. Those went up this morning. The video will walk you through how to use Excel to do the kinds of calculations that on kinetics kinds of problems that will help you on the exam. And the spreadsheet is a simulator that will let you decide what concentrations, what temperature you want to use for an experiment, and will give you the data. And I talk you through how to use that spreadsheet and how to take that data and then do analyses on it. This particular spreadsheet also, it's a practice sheet for you, and so it lets you put in whatever kinetic rate law you want for it to simulate, and then you can go in and see, if I analyze it, do I get the correct rate law from it, the correct rate constant, that sort of thing. So give that a shot, and definitely let me know if there are any questions about it that come up via Piazza in class or in the or in my office hours. Okay, tomorrow, Wednesday, there are content videos that are due as usual, and the small group activity quiz number 3 will be due as well. Friday, the homeworks as usual. Sunday, the Piazza participation cutoff. And then next week on Thursday, exam number 2 is going to get released. I now have a Piazza post up that has the topics list for the exam. I also have up formula sheets for both exam 1 and exam 2 so that you can look through those. For those of you that feel like there are just so many kinetics equations that you're having to deal with, hopefully that will keep it organized for you so you can see what the main ones are. Okay, some important details here. There are a couple of things that I've done in the synchronous class sessions lately that I want everybody to be aware of, so that if you would find them useful, you can go find those specific sections in the videos. They are indexed as usual in the on Blackboard for the timestamp, so you can go directly to them. In particular, Thursday of last week, I did an extended exam-style problem analyzing kinetic mechanisms and looking at how you would distinguish between different mechanisms for the same overall reaction. There was as well at the end of that class period another example of working through a kinetic mechanism, which I let the class work on their own, and then after some time working on it, we went in and looked at it. So that's a good way to get some practice on that sort of thing. Yesterday, on Monday, I did an extended walkthrough of a great deal of the small group activity number 3. So I know that there were a lot of questions on the derivations of the formulas and so on that are going on, so I went through all of those, and I went through how to easily within a Google Doc keep track of a formula that you're working on modifying as you go through it. And I also went through how to think about the various components of the questions that are being asked. So it is very much worthwhile, if you are still having some trouble with that group activity, to go through and watch yesterday's extended walkthrough that talks through a lot of that activity. One thing specifically I want to point out is that the original version of question 14 referenced question 10. That was a mistake. Apparently, I ended up adding some other questions earlier on and didn't update the number in the reference. It should be referring to question 13. Hopefully that will seem clear. And I already mentioned those two things. Do we have any logistical stuff people would like to talk about before we get into content? Okay. So we've got three main areas where questions were coming up in Piazza. The small group activity, one question that was still on some kinetics stuff, and then quite a few on equilibrium stuff. So people were asking specifically about some of these. I'm going to go over these relatively quickly right now to address them, keeping in mind that the really detailed analysis of all of these, if the quick explanation isn't enough, is available in yesterday's video of the class. So what I'm going to do is come over to this. Nope. Back. Let's come to small group activity. Okay. So can the chat see this okay? I don't know where my chat window went. There it is. That's where it is. Yes, wonderful. Okay. So, so the first question was, how do you identify the slowest step in the pathway? I'm going to zoom in on this a little bit so we can see better. So the numbers that you have underneath each of the steps is the half-life. And so the slowest step would be the slowest, the longest time that's listed here. So that's, if we look through it, going from uranium to lead, the slowest step is going to be that first step going from uranium-238 to thorium-234, because 4.5 billion years, which is what we have here, is by far the longest. There's another question that's asking for the second slowest step, and so that would simply be the second longest half-life that you have, which is going to be over here for the uranium-234 to thorium-230. There was a similar, there was another question someone asked down here talking about bringing the half-life into the equation. And the question was, let's see, I don't want to screw up my original here, so I'm going to make a copy. So someone was asking if the correct half-life equation is going to be, and so to show you how to put in a formula, insert equation, and now you have these extra things up here that you can use to make an equation. So for example, we can set something here with a subscript so that we can do T1/2 equals, you can come up here and put a fraction in, natural log of 2, over k. And so the question was about if this is the right formula to be using, but it was written out where natural log of 2 had already been plugged in, so 0.693. Oh, they always turn off numlock. 0.693. I do not recommend doing this, because when you're in the middle of doing an exploration of the formula to see how the formula ends up changing when you do some other steps to it to get it into a better form to work with, if you leave it as the natural log of 2, there may be cases where that ends up canceling with something. And so it goes away. Whereas if you've turned it into a decimal number, it won't necessarily be all that obvious when things are going to be canceling. Obviously, when you do an actual calculation using the formula, yes, go ahead and plug in 0.6934 for natural log of 2. But when you are trying to do the to work with the formulas, leave it in the symbolic form more so. Okay. The rest of the questions were about basically question 10, which is quite a few series of questions about calculating the amount of the isotopes that have decayed away or not. What you're doing in these cases is you are using the two equations that you get in questions 1 and 2, and question 11, which is an extended derivation here. The thing I want to point out about this one is that in part I down here, I give you what the answer coming up to that point should be, so that you can check to make sure you got to the right place. Which means that you can take this step and just move on from there if you're having trouble with the stuff that's earlier. If you want to see this in more detail, take a look at yesterday's class session. Okay, so with that done, I'm going to move on to the other topics that we have. So that's switched back, this back to .cam. Okay, so there was a question that was related to identifying in a mechanism catalysts and intermediates. And so the idea here is, figure out where my paper is. The idea here is that if you have a mechanism, a mechanism, so let's say A plus B goes to C, C plus B goes to D, then D plus A goes to, let's say, E, our product, plus 2B, okay? So if we add up what the overall equation is for this, we have 2A plus 2B plus C plus D goes to 2B plus C plus D plus E, okay? We see what cancels. The 2B's cancel, the C cancels, and the D cancels, so that the overall reaction is 2A goes to E. So what we notice is that there are three things that are part of the mechanism that are not part of the overall reaction. There's the B's, there are the C's, and there are the D's. Now, when we start these steps, we don't have any C to begin with. We form the C through that first step, and then it gets used up afterwards. So C is going to be an intermediate. The same thing is true of D. We don't start with any D, but as the mechanism progresses, we get some D, and then the D goes away. It gets used up. So D is also an intermediate. The B, on the other hand, is necessary to be there for that first step. It takes part in the mechanism, but then it's regenerated here at the last step. So it doesn't get used up, it just participates as it goes. So our B is a catalyst. Okay, so that's the distinction there between intermediates and catalysts. Do you need it there to begin with or not? And that was really the only kinetics question I ended up getting. Does anybody have any other questions on kinetics or this concept in particular before I move on to some of the equilibrium stuff? There are quite a few questions there. Okay, so let's go on to some equilibrium now. So the first question was figuring out an equilibrium constant from the kinetics. And so the idea here is we have some kind of mechanism, some kind of equilibrium, excuse me. Let's say we've got this. And we have a forward rate constant and we have a reverse rate constant. One of the things you need to, and let us also suppose that we know that this is an elementary step in both directions. So it is a single step process in both directions. One of the things you need to be able to do basically as a matter of course, as almost second nature, is to be able to write down the rate expression for a single step. So our forward reaction here, we'll label it R1, it's going to be our rate coefficient, K1, and since we know this is an elementary step, we know that we are going to have a collision between an A and a B. So we need concentration of A times concentration of B. And because the stoichiometry is such that we only have a 1 of each of those, the order for each of A and B is 1 as well. Okay. The rate for the reverse step is going to be K minus 1, R minus 1, K minus 1 times our product. In this case, our product for the forward reaction is our reactant for the reverse reaction. So our reactant is C, but there are 2 of them that have to collide, so we square it. So whatever your coefficient is in front, your stoichiometric coefficient for an elementary reaction, that becomes the reaction order. The concept of equilibrium is that the forward and reverse rates are equal, so that the amount of reactants and the amount of products that you have remain constant, not because the reaction's not going, but because forward and reverse are equal in rate, so the net concentrations stay the same. So this says that R1 equals R minus 1, or K1 concentration of A, concentration of B, equals K minus 1 concentration of C squared. Now what we can notice about this is that 2 of the things here are constants, and the rest of it are concentrations. So let's separate those out so that we can treat them separately. So we're simply going to solve this equation in a way so that all the constants are on one side and all the concentrations are on the other side. So K1 over K minus 1 equals concentration of C squared over concentration of A, concentration of B. This is what we call the equilibrium constant, KEQ. We have to note that these are the concentrations of these species once you have reached equilibrium. So if you start out with concentrations that aren't at equilibrium, you'll have either the forward or the reverse reaction happening faster than the other one, and the concentrations will shift until they reach this ratio. And the thing to notice is because this side here is just constants, at equilibrium, this ratio of concentrations is a constant. So if we know the equilibrium constant, and if we know 2 of these concentrations, we can calculate what the third concentration has to be for it to be at equilibrium. That's the power of the equilibrium constant. Now, it is convention that when you do this solution, the forward rate constant is in the numerator and the reverse rate constant is in the denominator. which means that over here in the concentrations, it is the products in the numerator and the reactants in the denominator. Okay. So you see, if we divide through by k minus 1, for this to go over this side, we divide through by A and B to go over to this side. So having the forward rate constant over the reverse rate constant means that in the concentration side, it's the products over the reactants. Now, in the content video on the equilibrium constants, I went through an extended example where the equilibrium wasn't using wasn't an elementary step in each direction, where there was an equilibrium in the first step, there was an equilibrium in the second step, equilibrium in the third step, and then that whole set of equilibria resulted in a net overall reaction that was in equilibrium. And what that analysis showed us is that we can write the equilibrium constant as the ratio of products to reactants, just as if it were a single-step mechanism, because all of the intermediates and the catalysts and all of those various things canceled out as we went through it. So what we have is that whatever your reaction is, single step or not, A to A, B, B, C, C, in equilibrium with D, D, E, E, F, F, however many you want, whether this is a single step or a multi-step reaction, we can write the equilibrium constant as concentration of D to the D power, concentration of E to the E power, concentration of F to the F power, over concentration of A to the A power, concentration of B to the B power, concentration of C to the C power. So that actually makes equilibrium a lot easier to deal with than kinetics, because in kinetics, the rate law does not have to follow the stoichiometry of the reactants if it is a multi-step mechanism. And so you have to worry about, is it single step, is it multi-step, in order to figure out anything about what's going on. But for equilibrium, you don't have to worry about that, because the same formulation works for both a single step and a multi-step process. So the last subtlety that we have in defining this equilibrium constant is that if, well, we are assuming here that these things are solutes, so maybe something like aqueous, okay? But if one of them is a solid, say, so imagine that you have a solution that is reacting with some solid salt that is sitting at the bottom of the beaker. What is the concentration of a solid? Well, the concentration of a solid is a constant. It is a value that just depends on what's the density of that solid. You don't change the concentration of the solid at all. And so that, in this case, if this is a solid, then this thing right here is also a constant. And so we don't want to have to worry about that, so we just move it over to the other side and fold it into the thing we're calling the equilibrium constant. So our equilibrium constant excludes on the right-hand side anything that has a constant density. So that would be a solid, and that would be a liquid where it's the solvent in the reaction, because over the course of the reaction, the solvent is at a much, much higher concentration than any of the solutes. And so the concentration of the solvent doesn't change appreciably as the reaction occurs. So that's the subtlety there. Are there any questions on how to write down equilibrium expressions and where they come from? No? Okay. So let's see here. What is it, how is it structured, and how do you use it? Okay, well, we will get to how we use it in a moment when we get down to the ICE tables. So we will come back to that. There was a specific comment about what I just went over. Newton said to leave out solids. The video said to leave out both solids and liquids, and so which is correct. And the answer is both solids and liquids. So Newton missed the liquids part of that problem. Yes?
Is it only leaving out the liquids though that have a constant concentration, or all liquids?
It would be all liquids. Yeah, so for example, if you were looking at a reaction like H2O liquid in equilibrium with H2O gas, so we're looking at vapor pressure here, right? The concentration of the water in the course of the reaction doesn't change, even though the amount of water might if a lot of it's evaporating. But you're decreasing both the amount and you're decreasing both the mass and the volume at the same time, and so the concentration stays the same. So the equilibrium constant for this would just be concentration of H2O gas. Or if you're doing it in terms of pressure, the partial pressure of H2O vapor. So, so any liquid is going to not participate. It is not going to be part of the equilibrium expression.
So what's the difference between that and what you just did?
Up here,
Yeah.
There's not really anything different.
But you didn't leave those ones out.
I left out. Oh, the aqueous portions? Well, here this is talking about the solute.
Okay.
Right. This isn't the water. This would be the thing that is dissolved in the water.
And you're talking about leaving out like the solution.
The solvent. Yes. So if you have a reaction like so H2O liquid, is in equilibrium. This is going to be a very important reaction for us later. OH minus aqueous plus H3O plus aqueous. Okay. So this is the autodissociation of water, and water molecules just sitting in a glass automatically are in equilibrium with the hydroxide ion and the hydronium ion. The hydronium ion over here is the hallmark of an acid. The hydroxide ion is the hallmark of a base. And in this case, you have the equal amounts of the two. And so they are, so water by itself is neutral because equal amounts of acid and base, which kind of cancel each other out. But if we look at the equilibrium constant for this, it's going to be concentration of OH minus times concentration of H3O plus without the water participating in it. So the solutes are part of the equilibrium constant. The solvent is not. Okay. Okay. All right, I put something in the video that I probably shouldn't have put in there. One of the issues with equilibrium constants is that their units are going to depend upon the reaction stoichiometry. So if each one of these things is, let's get rid of that one since I already have it drawn over to the other side. If each concentration here is measured in molarity, then what we have, our units are going to be molarity to the D plus E plus F over molarity to the A plus B Or putting it another way, molarity to the D plus E plus F minus A minus B. Right? So in this case, for example, the units of this equilibrium constant are molarity squared. The units for this equilibrium constant that I have here is going to be unitless because we have molarity squared in the numerator, molarity squared in the denominator, and it cancels out. So there is no single set of units for an equilibrium constant. It depends on the reaction stoichiometry. And so trying to illustrate that, I put this expression here in, and basically what that's doing is saying the stoichiometric coefficients of the products, sum them up, minus the sum of the stoichiometric coefficients of the reactants, and that becomes X, which is this power that you're raising molarity to get your units. This is a confusing way to write it, so it may be better to think of it in terms of the examples that I just described rather than that formula. We okay with that? Any questions on that? Okay. All right. Reaction quotient. How do you calculate and what is it? So the way to think of a reaction quotient is that it is of exactly the same form as the equilibrium constant. It's just that the concentrations you're plugging in may not be at equilibrium. So here I specified that the equilibrium constant is the concentrations of these species once equilibrium has been reached. That's important because equilibrium is when the forward reaction and the reverse reaction are happening at the same rate. If your concentrations are not at equilibrium, then those rates will not be equal, and so the step of making these two things equal to each other won't happen. Or they're not equal to each other. The rates are not equal to each other. The way to visualize that easily is to say, let's say you don't start with any C. What you do is you start with just A and B, you pour them together. Well, you're not at equilibrium because you don't have any C at all. So KEQ is equal to Q when the reaction has gone to equilibrium. So if we have an example, A plus B goes to 2C, and we have KEQ is concentration of C at equilibrium squared over concentration of A at equilibrium, concentration of B at equilibrium. Then Q is concentration of C over concentration of A, concentration of B, where we're not specifying that it's at equilibrium. What is Q important for? Well, we can divide the situation into three categories. If Q happens to equal the equilibrium constant, then that tells you you have reached equilibrium. If Q is greater than the equilibrium constant, then that means that the numerator of Q is too big, or the denominator of Q is too small relative to equilibrium. Does that make sense? If this is bigger than that, then you can think of it in terms of the numerator being too big or the denominator being too small. The numerator is the products. So it's saying you've got too much products. The denominator is the reactants. So it's saying you don't have enough reactants. So Q greater than KEQ means the reaction is going to shift that way in order to go towards equilibrium. That makes some sense? And the third category is simply the opposite of that. If Q is less than the equilibrium constant, then compared to equilibrium, Q being too small means that the numerator is too small or the denominator is too big. So, by the same argument, you have either too little product or too much reactant to be at equilibrium, and so the reaction will shift towards equilibrium by removing reactant and creating product. This right here is the general, if we generalize this idea, this is Le Chatelier's principle. Le Chatelier's principle says that when there is a dynamic equilibrium and you disturb the system in a way by adding something to it, changing the temperature, changing the pressure, something like this, then the equilibrium position will shift in the direction to reduce that effect, the perturbation that you made, the disturbance that you made. So let's think about that from an example. If we are at equilibrium, so we have the correct concentrations for C, A, and B for equilibrium, and then we pour some C into the system so that we now bump up the amount of C that's there. What has happened to Q at that point relative to the equilibrium constant? Is it now too big or too small? It'll be too big. If we've added C, that makes C bigger. So that is now, the numerator is now larger. Well, now that the numerator is larger, we now know we're in the situation where the reaction is going to shift to the left to create some more A and B and use up some of that C that was added until the ratio defined by the equilibrium constant is once again at that equilibrium constant. So adding C to the system reacts to reduce the amount of C that was added. You can apply that same idea to things other than concentrations. So for example, if this is an exothermic reaction, what does exothermic mean? Is it producing heat or absorbing heat? Producing heat. So we can write that as plus heat. Now let's suppose we increase the temperature, which you can think of as adding heat to the system. So if you're at equilibrium, but then you add extra heat by raising the temperature, which way is the equilibrium going to shift? It's going to shift to the left to minimize that the perturbation that was added. Okay, any questions on reaction quotient and on Le Chatelier's principle? Okay. All right. How do you tell which direction a reaction shifts? So that's what we just went over there. So it is in fact directly connected to this idea of the reaction quotient. Okay. More questions, starting to get into ICE tables. So in looking through the video, it looks like some people were having trouble identifying where the numbers are coming from, knowing how, when X is going to be negative, what equations are equals, basically the whole thing seems confusing. So what I'm going to do is I'm going to share screen here, and I'm going to I'll do that in a second. I'm going to call up the video so that we can look at the same screens that we have, that are the same examples that are shown here. So equilibrium, ICE tables. Okay. So let's start with this first example here. I'm going to try to maximize the screen, and I'm going to share screen here. Okay. So can folks in the chat see this okay? Oops. Okay. Cool. How do I get rid of that? Okay. So whatever reaction we have, we write across the top of our ICE table. And it's always a good idea as well to write down the equilibrium constant that you're dealing with. So this is something that you should be able to get just by looking at the stoichiometry of the reaction. Products over reactants, you put each product that is a solute or a gas in a concentration up here, and you raise it to the power of the stoichiometric coefficients. Remember that the solvent itself does not participate in the equilibrium constant, so I've grayed out that column as a reminder that we don't do anything with this. Okay, we now have initial change in equilibrium. Initial is the information you're given in the setup of the problem. And in this particular case, we are told we are starting with 0.2 molar acetic acid. Okay, so moving forward until we have that in, okay. So we have 0.2 molar acetic acid. And so I make the comment that you're going to want to have everything in this table in a common unit system. So if you're dealing with an equilibrium constant in terms of partial pressures, it might be atmospheres, it might be torr. If you're dealing with concentrations, it will usually be molarity. But putting up here what that concentration is a convenient thing to do just to make sure that you're staying on top of what the units are. Now, the setup of the problem here is we make a solution that is 0.2 molar in acetic acid, which means that we are adding acetic acid to get to that concentration level, but we're not really starting with any acetate or hydronium ion that we need to worry about. Now, a subtlety here that you shouldn't worry about yet, but so that you don't later on say, hey, you lied to me. Water naturally does have some hydronium ion in it because of the autodissociation of water I showed you earlier, but it's a small amount, and if you've added acid to it, then that's going to end up being a negligible amount. So we will deal with that a lot, I think, next week when we're getting into that. But for the present purpose, we assume that we are starting off with zeros for those. So we have zeros in that case. Now, this would define our Q, not our K, because this is what we added. It's not after we have allowed it to get to equilibrium. So we now need to ask ourselves, which direction is the reaction going to go? Well, it cannot go from right to left, because we already have zeros written for the acetate and the hydronium ion. We would end up with negative concentrations if we used up acetate and hydronium, and that doesn't make physical sense. We cannot have a negative concentration. So the only possibility is for the reaction to go to the right as it approaches equilibrium. So that means that we need to put in, if we call X how much the reaction happens, so we have an amount of acetic acid that goes away, producing the acetate and the hydronium. The stoichiometric ratio between acetate and hydronium is 1:1, so both of these are going to be X. The acetic acid is going down instead of going up, and it's going to go down by the same amount that the acetate is going up by, because it's a 1:1 ratio. So the change line here for acetic acid is going to be minus X. However much acetate went up, which is X, is going to be how much acetic acid went down. The equilibrium line is simply initial plus the change. So we add it down, and we get 0.2 minus X for the acetic acid, X for the acetate, and X for the hydronium. We now say this is at equilibrium, which means that our equilibrium constant up here applies. So what we do now is we plug in these expressions for these concentrations. So I'm going to move here. So I brought down the equilibrium constant, the value, which is, it would either be given to you or you'd be given a way to measure it. I bring down the concentrations at equilibrium. So the acetate ion concentration at equilibrium is X. The hydronium ion concentration at equilibrium is X. And in the denominator, the acetic acid equilibrium concentration is 0.2 molar minus X. Okay. Do a little bit of algebra. And we get down to here, and we find that we have a quadratic equation. So a quadratic equation, you will hopefully remember from algebra, means a second order polynomial with a coefficient in front of x squared, a coefficient in front of x, and a constant set equal to 0. I got a specific question from someone on the on Piazza. I'm going to stop sharing for a second, switch back over here. I got a specific question from someone on Piazza about that step, going from this expression to the value for x. What happened there was I was assuming that you remembered from algebra the quadratic formula, which is ax squared plus bx plus c equals 0. And so we find that x in this case equals negative b plus and minus the square root of b squared minus 4ac all over 2a. Okay, so hopefully you will remember that from algebra. So those are just the coefficients that we have. And in this case, the coefficient of x squared was 1. The coefficient of x, meaning the b, is 1.7 times 10 to the negative 5th molar. And c, the constant, is negative 3.52 times 10 to the negative 6th molar. And so that gets plugged into this formula. Because it's a quadratic, there are two solutions. There's one of them when you use plus, there's one when you use minus. And so I'm going to switch back over here. And you see here that there are two solutions that come up. The negative one does not make sense because that would be a negative concentration for some things, so it has to be the positive one. And so we now know that the acetate ion concentration at equilibrium is 0.00187. That's the same as the hydronium ion concentration at equilibrium. And the acetic acid concentration at equilibrium is the 0.2 minus that. So it's going to be about 0.198 molar. Okay. So that is going through an ICE table. So the general strategy is write down your equilibrium constant expression so that you know you know which concentrations you're needing to worry about. You write down the balanced chemical equation, initial change equilibrium. You set up the initial conditions based upon the problem statement. You figure out which direction you think the reaction is going to go. And you assign X to the extent of reaction. So you put in an X saying if 1 mole of the reaction happens, then based on stoichiometric coefficients, how many moles of these products do we get? How many moles of the reactants go away? And so you modify this change line based on the stoichiometry and based on which direction the reaction is going. Simply add the two first rows together to get the equilibrium. Those are the concentrations that you're plugging in to the equilibrium expression you wrote earlier. So you do it, and you solve for X. That's the general strategy. There was a follow-up question about the same kind of thing, particularly in this case when we are talking about the solubility product, where the follow-up was, how does knowing the answer show you when the solution is saturated, and what does saturated mean? So the idea here is that if we look at the reaction that we have written, we have the solid in equilibrium with the ions that have dissolved. What is the definition of solubility? It's the amount that is dissolved when it is in equilibrium with the solid. So if you are below saturation, if you are below saturation, then you will not have enough for there to be a solid that's present at all. So stating that there is an equilibrium is stating that you have a saturated solution. So the procedure that you follow here is exactly the same as the procedure we did a moment ago. You write down what your solubility product is here, and notice that we have a square here because the stoichiometric coefficient of the fluoride ion is 2. That also plays a role right here because for every magnesium ion that is formed upon the dissolution of magnesium fluoride, 2 fluoride ions are formed. And so when you plug in the equilibrium values to the equilibrium expression, you both have a 2 here, coming from this, and it's squared because the KSP is squared. And then you can solve for your X, which gives you the concentration of magnesium, and twice X gives you the concentration of the fluoride. Okay. The last subtlety that was asked about in the questions was when we got to this example where we were looking at a shifted initial state. And so for anybody that has not looked at this video yet, let me explain this a little bit. So here we have a problem we're trying to solve where we have some copper-2 ions, we have some ammonia, and we're trying to see how much of it will form this particular complex ion in solution. And so the way we would set up the problem based on what we've talked about so far, we have our equilibrium constant expression up here. We have 0 of the product initially, so we would put X's over here, and we end up with this expression, which ends up being a fifth order polynomial. So it's pretty nasty polynomial. And if you plug it into something like Wolfram alpha, like I suggest in the video, the answer you get is almost identical, unless you go out to a ridiculous number of digits here, to the amount of the copper-2 you started with. Which means that if you want to know how much copper-2 there is that's left, can you really trust these numbers way down here? Probably not. So we need an alternate strategy to be able to handle this kind of situation. So what we do instead is we notice that this equilibrium constant we have here is absolutely enormous. 5 times 10 to the 13. That's huge. That is 50 trillion. Okay. So that means that the numerator of this is going to be huge compared to the denominator. This is what is known as a product-favored equilibrium. So you have a lot of products and you have almost no reactants. So if we're looking for small deviations from it being like all products, that's where we ought to start when we're doing our calculations. So what we're going to do now is shift our initial conditions. Let's assume that the reaction goes all the way over here as far as it possibly can. So if all of the copper 2 reacts away, then this concentration goes up by that same amount. So the 0.01 becomes the 0.01 here. And the amount of ammonia goes down by 4 times how much the copper went down by. So it drops from 1 to 0.96. At that point, we now know that we are probably close to equilibrium. So, but the equilibrium, we went a little bit too far, only a tiny bit, but a little bit too far. So the equilibrium is going to shift slightly to the left, and so we have a negative x on this side, positive x on this side, and a positive 4x here because of the stoichiometry. We can add them down, just like we normally would. But here is where the magic happens. At this point, because we strongly suspect that we are really close to equilibrium already, x is going to be small. And because x is small, that means that 0.96 plus 4x is going to be 0.96 plus something really, really small. We don't have that many significant digits. Let's just drop the 4x. Same thing here. It's probably going to be small compared to the 0.01. So it's 0.01 minus something really small. So let's drop the x and make the math easier. At that point, we can now write our equilibrium expression. Again, we're using this equation up here. And because we've canceled out, we've knocked out those tiny little changes, our formula here is easy to do. You can do it on a normal calculator without having to deal with a 5th order polynomial like you did before. Just multiply through by x, divide through by 5 times 10 to the 13th, and then calculate. You figure out what that is. We find x is 2.4 times 10 to the negative 16, and you check yourself. You check to make sure that the assumptions you made that you could ignore 4x and you could ignore x here is valid. 2.4 times 10 to the negative 16, that's so far down in the decimal places that yes, we can absolutely ignore that. The textbook says that if the x you're dealing with is 5% or less than the number that it's being compared to, then that's an okay approximation to make. I find that kind of arbitrary, the 5%, but if you've got to have a cutoff, sure, why not? I'm not going to give you cases where where it's like 5.1% or something like that. I'm not going to give you borderline cases like that. Okay, so that is equilibrium. I know I talked for quite a while there. Let me now open things up to questions, if anybody has questions on any of the equilibrium stuff we were just talking about. We have about 10 minutes, 8 minutes. Yes? Yes, it can still be. So the question for the people in the chat is, the procedure of dropping the x, can you still solve it without dropping the x? Yes. And so if you would rather just go plug it into Wolfram Alpha and do that, perfectly fine. I wouldn't want to try to do it by hand, but yeah, the math is right. The only thing is that if you are wanting to be able to solve, if you're wanting to be able to have an easier mathematical solution, the sentence is getting away from me, then that's the way to handle it. But yes, you don't have to make that approximation. Chat question. It's my understanding that question 14 I answered in the video. We may be able to, so 14 on the small group project, right? So question 14, let me pull that up. I will, why can't I get rid of that? Okay. I will share screens. And let's go over here. All right, question 14. So there was a typo originally in this question. Originally it said question 10 here. Question 13 is the one you want. And what this is doing is saying, suppose that 10% of the lead 206 had leached out through micro cracks. What would its new ratio be? So let's find our initial ratio, which we find is right here. So what I would do to address this question is put, I'm going to put a formula in here. Insert equation. We're doing a ratio. So we are doing that many moles of 206 PB. I'm not going to deal with this superscripts right now, per 1 mole of 238 uranium. Okay. So since it's just a ratio, pick a reference amount that's convenient. So if you have a mole of this and you have 0.968 moles of this, then the molar ratio between the two is the 0.968. And we're saying 10% of the lead leached out. So that means that the numerator is going to be multiplied by 0.9 because 90% of it's still there, and the denominator is going to be multiplied by 1 because none of the uranium leached out. And that's it. That's how you find the new ratio, just by looking at the old ratio and how much of one of them leached out. Yeah, you're welcome. All right. We have about 5 more minutes if anybody has anything else. I'm happy to talk about anything. Yes?
Can you just show how to get to the kinetic video that you posted?
Yes, absolutely. So let me move this. Let's come. All right, I'm back to Blackboard. All right. Here we go. So if you go into exams, we have a midterm exam 2 folder now. So the equation sheets are linked here. The spreadsheet that is the practice kinetic simulator is here. And this is a link to my YouTube channel where I have the tutorial that takes you through both how to use Excel in general for these kinds of things. Because I know some people have expressed that they don't have very strong Excel skills. So I walk you through how to think about doing simple calculations in Excel and to save time immensely with it. And then I also go through specifically this kinetic simulator spreadsheet so that you can see how it works. as well as figuring out some examples of taking some data from that, putting it in your own spreadsheet to figure out, is it zeroth, first, or second order, figuring out how can I find the rate coefficient from it, how can I use the method of initial rates, how can I use the method of flooding. I go through examples of all of those in this video. Let's see, when's the next midterm? Yes, opens on Thursday of next week and goes through that Sunday. That's correct. And the midterm is going to be about 2/3 kinetics, 1/3 on this week's material on equilibrium. We do have more equilibrium stuff we're going to be doing for the next couple of weeks after this, but the up through ice tables is as far as we're going for the exam. All right, thank you all very much.